Okay, so we're back for third lecture on ocean circulation models. Jacques was pretty clear about this idea that I should stick to the schedule a bit more tightly, so I'll try to go as fast as possible. And please don't hesitate to interrupt me if I'm not clear enough. So we're going to talk about, well, that's more putting together a set of random thoughts about things that I think are actually changing in the way how we perceive ocean circulation models right now. Those things might, in some respect, sound very familiar to most of the audience here, because most of you here are aware of how we use ocean models in operational systems, how we deal with uncertainty in operational systems, and how we use data assimilation in operational systems. But this awareness is probably not shared at the same level in a wider, broader community of ocean modelers. So I think it's probably interesting for me to let you know how the way how people are considering ocean model is gradually changing, and this is certainly something that comes from the interaction with operational applications. Okay, I will not explain what I said in my previous lecture. Just let you know that I try for the next 35 minutes. Is that right, Jacques? Okay. For the next 35 minutes, I try to actually talk about the ill-posed nature of deterministic geoscientific modeling, how stochastic closures are actually changing significantly some of the biases we thought we would live forever in ocean models right now, how stochastic modeling can help and deal more generally with a wide range of uncertainty in ocean models, and that this combined with ensemble simulation allows to tackle new questions that we thought we didn't have tools to look at. And this overall advocates for this idea that we're gradually switching from considering ocean circulation models as deterministic models to thinking that we're more dealing with engines that allow us to estimate probability of states given some observations and some uncertainties. And I'll briefly try and let you know a couple of remarks regarding what we could get from data science in ocean modeling. Okay, so once again, an outline. I'm talking about stochastic modeling in ocean circulation models, talking about the notion of uncertainty in ocean circulation models, talking about this transition towards a probabilistic ocean modeling through the use of ensemble simulations, and talking about what is emerging, I think, this idea of more data-driven development of geoscientific models. Okay, stochastic modeling in ocean circulation models. So for those of you who've been waiting for a lot of details there, I'll be very quick. I've actually simplified a bit the lecture over the break. So just to be clear, we're talking about. I mentioned a couple of times during my previous two lectures that assuming that you can draw a local deterministic model that allows you to estimate the impact of unresolved states onto resolved scales locally and deterministically is certainly a very strong assumption, and that physically it's pretty much equivalent to saying that basically whatever the microscale, the detail of the microscale, the way how they would impact the macro scale, the large scale, is only constrained by the large scale, and by no means this is verified in any fluid flow. So this is certainly a very strong assumption. And it turns out that a number of recent works in oceanography, following previous work in other fields, including atmospheric science, are gradually reconsidering this assumption. This is usually done through the idea of transforming closures into weakly constrained closures. So this idea that instead of saying, well, A implies B, I would say A implies B, maybe. So I'm just adding some noise on top of that, allowing some randomness to be introduced in the system through stochastic procedures, therefore accounting for possible variability of the upscaling flux at the macro scales. Okay, So it seems that the recent literature, and it has been, if you're looking a bit about, if you're reading a bit ocean modeling, the journal, you would probably have seen that the number of papers mentioning the word stochastic in the title have been rising dramatically over the last 2 years, and that basically there are two fields where it is now quite established that stochastic closures can bring something to ocean modeling. There's this idea of stochastic closures being able to allow to represent much better those exchanges of energy from the unresolved scales to the large scales. And what is good there is that your stochastic closures allow to put some energy sometime, but not always. Therefore, allow you to get a stable numerical scheme, stable methods, although you're constantly injecting energy from unresolved scales to the large scale. So that's one of the reasons why it's really key there. And also, notable, but I mean radical, substantial improvement of Gulf Stream dynamics has been obtained through simply looking at a term nobody has ever looked at before, basically taking into consideration the fact that there's a nonlinearity that we're not looking at in ocean models. It's the nonlinearity of the equation of state, and that there could be upscaling through this nonlinearity, and that a good way to account for this upscaling is through stochastic procedures. So this has been used in forced models and in coupled models, showing substantial response in all the cases. Okay, so that's when you look at stochastic modeling as a surrogate or an extension to subgrid closure. But you can actually look at that from a wider perspective. And there's actually another rationale that supports the idea that we should put more random perturbations in geoscientific models, and in particular in ocean models. So this is this idea that the actual topology of the phase space of an ocean model might be very complex, and that your system, your state, may be stuck in some local minima of some potential, and that the system being stuck there maybe is just a happenstance, maybe it's not something that is constrained by your observation, but maybe that's something that you're not happy with. And therefore, you want to give the freedom to your system to get out of this wheel. Okay? You want to give the system the freedom to explore a wider range of possible states. And that's probably one of the ways how it has been introduced for operational purposes in atmospheric forecast, and developed further in particular by authors like Tim Palmer. So if you take this perspective, basically you're no longer only dealing with using stochastic closures. You're talking stochastic modeling for accounting for uncertainties, and therefore you can account for a wider range of uncertainties than just subgrid closures. And among those uncertainties, there have been a number of demonstrations in the recent literature, but there are convincing results supporting that it's a good way for accounting for uncertain parameters in sea ice models. It's also a good way for accounting for uncertain parameters in biogeochemical models, which we all know are only weakly constrained by observations. So basically, there's a shift there. There's this feeling that maybe there's something very powerful in those stochastic approaches, because it changes the actual mean state of the system. But very substantially, people have been spending years dealing with the detail of eddy closures without actually seeing a difference in realistic settings. And out of the blue, people starting to play with stochastic closures, they are actually breaking some of the long-standing biases that we had in ocean models. So that's something big that is happening here. Okay, so we're just talking about uncertainty, saying that stochastic modeling allows to deal with uncertainty, but maybe we should describe a bit more what is it we're talking about when we talk about uncertainties in ocean circulation models. Okay, so there are actually several sources of uncertainties, several sources of errors in this discretized representation of ocean dynamics. And the first of them is obviously the fact that we don't know the state of the ocean. We don't know what the ocean really looks like, even at the scale that we want to prescribe the model at. So same, even in boxes of 100 kilometers times 50 meters, we don't know exactly how the ocean is. So there's an error there. So that's a very substantial error because remember, the ocean is, I mean, the dynamical equations are their nonlinear equations, and therefore they could transform any small error into something big. Okay, there are upscaling mechanisms there. So first, uncertainty in initial conditions. Obviously, if you wait for long enough, probably the sensitivity to the initial condition is probably lost by the system, and you're more than governed and driven by the forcing. So the forcing is the second source of uncertainty in ocean model, because we're using uncertain atmospheric fields and uncertain parameters in the bulk formula I was talking about 2 days ago. Ocean model solutions are also affected by the errors, we've been discussing about that, in subgrid closures. Closures are obviously imperfect models and most of the time weakly constrained in terms of their parameters. So ocean models are also, say, affected by something that we often overlook a bit, the fact that basically the real dynamics is not following the primitive equations. There are other terms that we have neglected, one of them being the non-traditional Coriolis term due to this thin skin approximation. So there are many things that we're missing here, plus the fact that we're discretizing the PDEs. And we know that we're making systematic errors when discretizing the PDEs. So that makes a lot of errors. And if you really look at that, you start to understand that it's not a happenstance. It's something that is consubstantial with the modeling we're doing. Uncertainty is something that is there. It's real. It's a part of the model. That's a property of the model. So we need to take it into consideration when we're modeling. Okay, so that's the first step towards this paradigm shift. Okay, just illustrating a bit more why numerical errors are so important. So just without writing too many equations here, without writing any equations actually, just I guess most of you know that there are different types of numerical errors. I've been mostly talking about dissipative numerical errors so far in defining this notion of effective resolution, for example. Actually, there are different types of numerical errors, and you can broadly categorize them. One more category, list. I like lists. On the first hand, you can talk about the dissipative errors. So all the errors that in your evolution equation will tend to affect the amplitude of the signals, and also all those errors that would tend to change the phase of the signals. So we're here talking about dispersive errors. And what is key that you need to keep in mind is that those errors, they can propagate in the system. I mean, those deviations, they are advected, they live, they follow also a certain dynamics, and therefore they can also accumulate in time. And which means that in the long term, what you're dealing with is something that has no longer this particular vague idea that you could have that an error is something local. No, it has patterns. It can be large in certain places, small in others. We're talking coherent, large-scale structures when we're talking numerical errors. Okay? Now, in practice, how does the error translate into your ocean model solution? Well, obviously, as an oceanographer, you care about, I mean, you use ocean models for looking at the variability, the trend, and the mean state. And the three of them can be affected by model errors, by modeling errors. And it's quite important to keep in mind that those errors are spatially correlated. For instance, what you see here is just coming from a study a couple of years ago by Angélique Melève. So just showing here a profile in a certain region of the ocean of salinity in a model versus ensemble of profiles coming from a Coriolis database. So basically, what you see here is the fact that the model is not salty enough at depth, but at the surface is too salty. So there's a structure there. There's systematically regions where, I mean, large regions where it's very salty and large regions where it's not salty enough. So there's structure. There's correlation in the errors, and that's something interesting because if there's structure, it means that maybe we'll be able to describe this error with a limited number of degrees of freedom. So that's key for what will come later. Okay. Examples of how errors could actually translate into affecting the signal you look at in models. So what I've shown here, because Brian is in the room, is results from one of his study 5 years ago, looking at the universe cascade in time, in frequency space. This idea that we all know that energy, as I discussed earlier, is generally in 2D flows transported towards larger scales. There's actually a similar kind of phenomenon happening in time too. So a perturbation that is localized in frequency will actually grow due to nonlinear interaction and affect slower frequency. That was nicely shown here in Ensemble numerical simulations, and showing that basically there's a preconception that we might have to change. This idea that, well, okay, in forced model, obviously the phase of eddies is not good, but I don't care because the eddies are fast phenomenon, and therefore if I'm looking at slow phenomenon, it should be okay. Well, this is wrong, and we know that quite well now because of that sort of work and also because of the work of Thierry Panduf. We know that there's actually a substantial fraction of the interannual variability of the ocean that is driven by those nonlinear interactions involving mesoscale eddies and features, okay? Even up to decadal timescale. So this is just an illustration here saying that the fact that we don't have the phase right for eddies actually has an impact on things as simple as, I mean, as important as the fluctuations of the AMOC in a forced simulation over long time scales, okay? Another example showing that we really need to take into consideration this question of the uncertainty, talking about the AMOC again. So this is here an illustration coming from a paper by Eric Perens 4 or 5 years ago, where he looked at a number of simulations where basically was perturbing the freshwater flux in the northern Atlantic and looking at the way how the AMOC was responding to this perturbation. And since he was doing that in a forced ocean model, he had to specify this freshwater forcing I told you about. And he was curious enough to actually change this freshwater forcing a bit, just because no one could give him a very clear rationale as to what value he should be using. And by just changing this value, he actually changes the whole range of solution in terms of long-term evolution of MOC in his forced model. So basically saying that although there's quite acceptably or arguably some sort of predictability of MOC variations from years to years, if you look at the long-term trend in those models, it's totally governed by the freshwater restoring. One of the most weakly constrained parameter in an ocean model. Okay, so we're talking about a major uncertainty here, something that is big. It's not small. It's central to our models. Okay. Also, thinking about this again, about this idea of the complex topology of the phase space of a nonlinear system like the ocean, you have this idea that possibly you could have attractors. Okay, so places where it's hard to get out. So we also know that this idea of attractors is something that is key to understanding, say, very long time scale variability in the ocean, like when it comes to hysteresis of the MOC of a long time scales involving freshwater feedbacks, and indeed you can. If you combine theoretical works and models, you can end up and see that there are good indications that indeed in ocean models, as we run them right now, the MOC might be unstable to forcing perturbation and likely to lead to hysteresis kind of behavior. The problem is, can we trust this prediction? What is the real reason why we should believe that this model is not in a particular state? I don't know. So basically, the very basic question, the reason why we're doing ocean modeling might be very much affected by errors we've been just constantly setting aside years after years. So we need to take that into consideration. So that's where ensemble simulation come into play. Okay, ensemble simulation for this audience probably sounds like something very, very common. Obviously, since you all know what that assimilation is, you all know what the ensemble Kalman filter is. For those who don't know, basically the idea here is that instead of trying to put by force data within my solution and bring back my solution to the data. I just accept that there's a certain level of randomness in the possible states that my ocean could have. I describe this randomness through an ensemble of trajectory, and I let that evolve, and I just constrain the actual envelope of this PDF with the observations. Obviously, there are conditions for this to work, but basically the idea is that you're sampling the possible states of your system given your observation and your uncertainties with an ensemble of simulations. So whereas you're sampling a PDF here. So that's obvious to you, but that's not obvious to most ocean modelers who don't work with data assimilation. There's another situation where ensemble modeling is something that is pretty much accepted. It's when it comes to climate projection. And there, the idea is that by using the whole ensemble of climate models, you could actually reduce the possible uncertainty that is due to possibly one individual model having strong bias or a weird kind of sensitivity. So you're reducing the model uncertainty through ensembles. Okay, so that's something that we always do. Still, we don't do that. I mean, me as an ocean modeler, not doing data assimilation, I've written, I guess, tens of papers just analyzing one trajectory of an ocean model. It's only now, after a certain number of years, that I figure out that maybe I should have used more than one member. Okay, so a close colleague, Thierry Penduf, put up this idea that, well, okay, we haven't made so far ensemble modeling in ocean modeling for studying interannual variability of the ocean. Why don't we try it? Okay, we have big computers, we should try. So he basically came with this idea of instead of running one global eddy resolving simulation for studying the interannual variability of the ocean state, he would be running 50 members. And he would have to obviously create some spread among those members. He would do that through stochastic modeling, trying to adequately control the spread of his ensemble. And in the end, what he got is basically a time-evolving PDF of principal states of the ocean circulation, something that is consistent with the forcing, consistent with the initial state, but takes into consideration certain uncertainty. Maybe not all of them, but at least he can have a look at some form of uncertainty. And this actually allows to investigate very quantitatively what fraction of the ocean variability is governed directly by the atmosphere and what is spontaneously generated by this oceanic chaos I was referring to. So basically, the ensemble mean gives you an idea of what is robustly forced by the ocean. The deviation to this ensemble mean and say quantities built from this deviation can give you information as to what is the signature of the oceanic chaos. Okay, so if you're interested in those questions and if you haven't taken the opportunity of the post session to discuss with Stephanie and Isel, you should go and discuss with them. They would be, I'm sure, don't know where they are, very happy to explain you the result they got with this exciting numerical simulation. Okay, so just summarizing a bit is here. What are the actual benefits you can get from this ensemble modeling approaches? Well, a number. Where am I? Yeah, a number. The first is you have a very good and very cheap strategy to convince your supercomputing center that your model is actually scalable. It's 100% scalable. Okay, you have independent models. So if you want to for your application to use twice as much cores, it will actually produce twice as much data. It is 100% scalable. It sounds like a stupid remark here, but that's probably one of the possibilities we should keep in mind for actually using optimally the HPC resources I was describing in my previous lecture. Okay, second thing, I think it's more generally than that basically, and I discussed that a bit later in the last part of the talk, the fact that we're now switching to a vision where when we consider our ocean model as a machine to describe probabilities, allows to actually formulate questions in different ways, and in particular to deal with data differently, and to accept that our models are not only based on first principle physics, they are also trading off errors. Okay? And that's good because we do have things for trading off errors. It's data. So basically, our ocean models are no longer physics-driven models, but data-driven and physics-driven models. Okay? It has very practical thing that, from my team's perspective, is great. Is that we have a common language to talk between data assimilation experts and between ocean modelers. Something that might seem obvious for you who are living in this world where the two communities do talk. But for most of the ocean modelers outside this room, this is not something that obvious. So we do have a very powerful here concept for bringing people together, and that's important, I think. And the most important from a scientific standpoint, I guess, is this idea that now that you're objectively accounting for the uncertainty, and knowing that your observation also do have uncertainty, you can actually compare PDFs quite objectively. So there are a number of scores, and I'm sure that you all know those scores for the reliability, the definition of ensemble. Just here mentioning how rank histograms can help you and actually measure to what extent the distribution of your possible states as described by your observation or as described by your model fit. And if they fit, if you cannot distinguish the two, then it means that your model that your ensemble is reliable. So there are heaps of measures there, and I'm sure that you know that much better than me because I'm just an ocean modeler. Okay. This all advocates for this idea that we're switching to a more internalized representation of the work we're doing with ocean models as basically accepting that we're just modeling a system and that it's only a fraction of the real system. So the real system is what we can represent plus what we cannot represent. And we need to account for the fact that there are interactions between those two systems and that we cannot prescribe fully and deterministically those interactions. Okay. At the same time, there's also this idea that the states of the ocean system, so if you take a variable in the ocean, it's the real reason why you need an ensemble for describing its uncertainty, the range of possible states, is because it has no reason to be a Gaussian distribution. And in practice, in many cases, what you observe is that the distribution of a variable in the ocean is not a Gaussian. It can be multimodal. Okay, so you need ensembles for sampling you need ensemble members for sampling the PDF, and you need stochastic modeling for creating the spread. So that's something that is definitely changing the way how we do modeling right now. And blah 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 blah. So I think it's a paradigm shift that we're facing here in oceanography. Still, I'm obviously being very optimistic here, and there's one thing I haven't talked about at all is the fact that the number of degrees of freedom of the PDF you want to sample is massive. It's huge. It's very large. I mean, it depends on the problem you're looking at, but that's several tens of thousands, 100,000, billions, and you only sampling this with a 50-member PDF, a 50-member ensemble. So there's kind of a mismatch there. So obviously, there's a lot of science to be done. There are a lot of things to be thought of, and there's an exciting field that just opens here as to how you can actually sample possible states of the ocean with limited amounts of members. Okay, so I've tried to convince you that we've been through a transition with this idea of probabilistic ocean modeling. For the remaining 7 minutes, Jacques, I will try and convince you that there might be another transition coming. It's just a question mark that I'm asking. I think it's possible that our field may go through a transition due to how we're dealing with data. So let me explain a bit more what I mean here. So as you all know, and that's some sort of cliche, the flow of geoscientific data is increasing at an accelerating rate. Okay, we all know that. That's just stupid, but that's if you really want to understand what we're talking about, just a couple of figures might be useful. So keep in mind that throughout mission, the rate of downlink of data is 360 megabytes per second. To be compared with conventional altimetry, something like 30 kilobytes per second. So it's not an order of magnitude change that we're talking about here. It's 1, 2, 3, 4 orders of magnitude, right? So that's a huge change that we're talking about. Now, if you think about model data, we're pretty much, I'm purposely calling model data data, okay? So that's because it's just a kind of data that has uncertainty, not of the same nature, but it has also uncertainty as observational data do have uncertainty. Okay, so that's an important step into getting to data-driven science, I guess. So if you think about the models we've been discussing with Eric over the last couple of days, any of those simulations just produces hundreds of terabytes of data, which means that in practice, in every single scientific study you do, you're playing with a lot of data. Just go and ask Ishel or adequately how a problem that can be to deal with those data. It also means that in practice we need to design and use different, say, strategies for getting information out of those data, and different methods and pipelines for fluxing those data across our analysis. And you're probably all aware of the fact that this constraint, the fact that you have to think differently when you have a lot of data, have actually transformed profoundly, I mean, very deeply, certain fields around us. Some scientific fields are just totally different. They have been revolutionized because of this. It sounds like a cliche, but go and discuss with people involved in genomics, in neuroscience, and probably also people involved in social science. Discuss with them, and you will understand how much of a transition they've been through just because of the availability of data. So the question I'm asking here is obviously whether this flow of data would actually not only change how difficult it is to do the science we do, but also change the way how we do the science we do. So let's think about that a bit more carefully. How do we use, say, for instance, observational data in ocean modeling, in oceanography? So how do ocean modelers use observational data? Well, they use it for constraining initial states for their models. Okay, most of the time, and very often now, this information is coming from ocean reanalysis. They use data for constraining the forcing function, in particular at the surface, for their ocean model. So this is based on atmospheric reanalysis on the one hand, and satellite data on the other hand. Okay, so initial state, forcing. Then they run the model, and in the end, they use the data to say how good the model was. Okay, so that's just for assessment purpose. And how seriously they get into this exercise of assessing the model, it depends a lot on how penny picking the reviewer is. Okay. In the best cases, you could have also imagined, but that's not always the case, that in this particular model you've been using, one particular subgrid closure has been calibrated against observation and maybe developed after a field campaign. That's probably maybe one of the 4 or 5 of the closures we're using in an ocean model. And if you're happy enough, maybe the representation of fine-scale processes have been assessed carefully with observation with this particular model. But that's not for sure. So basically what I'm saying is that we're using data kind of, well, that's a bit boring. That's very straightforward the way how we use it. But there are innovative approaches. Some people have been using data differently, and the more those approaches will emerge, the more natural they will seem. So, for instance, you all know that you can use you could constrain parameters for subgrid closures with approach inherited from data assimilation, and Jacques has been involved in that quite a while ago already. You can also use observational data this time for actually constraining parameters you don't know in your model, as for instance the parameters in the bulk formulae. That's something that actually works. You can also you could also think about using things like a byproduct of the production of notion reanalysis, this idea that you have fields of increments of data assimilation schemes. So basically, every single time the data assimilation scheme tries and drag the model towards the observation, since it's dragging the model towards the observation, it means that there's something that is dragging the model away from the observation. So that's an error. So that's a way to understand the error. If you understand the bias, you understand the errors. If you understand the increments, you understand the errors. So this is something that has been tried a couple of times with convincing results in certain circumstances. So arguably, I think ocean model design and the use of ocean model will change, in particular with this idea that we have a lot of data and we can do more things with it. The distinction between an observational data and a model data is gradually disappearing. What is reanalysis? Is it observation? Is it model? I don't know. So basically, we're going to invent new ways of playing with the data. So just to give you 2 or 3 examples of why I think this is going to happen very soon. So this is here a plot coming from a paper done by colleagues in Grenoble 2 years ago. Those people, they are experts in fluid dynamics and the modeling of turbulence. Okay, so what they do all day is building closures for LES. I personally find it interesting a bit. It's quite soon a bit boring because it's always the same problem, but they do that a lot, and they are real experts in the field. So they try and guess how they could constrain, say, a subgrid scale of tracer, given a certain knowledge of gradients at large scales. Okay, and they try to do that. And what they've done over the recent years is instead of thinking very deeply about the mathematics and what should be the governing principle, the first principle of physics, they just build data sets. They do DNS, large number of possible states, then they count the number of free parameters they could constrain with the size of their data set, and they design a model that has the right number of parameter, and then they run a big machine learning technique to estimate those parameters. The problem is, it works much better. It works much better than all what people in this field have been doing for 30 years. So you might say, well, okay, this has nothing to do with physics. There's no first principle understanding there. Still, it is changing this field very fast. Another example of this is a paper in JFM last year, so Journal of Fluid Mechanics, looking at a pretty similar problem, but in terms of Reynolds average Navier-Stokes modeling of momentum closure with deep neural networks. So those things are happening in a community that is not that far from ours. People we would have thought would have been more reluctant than us to use that. And obviously, you all know that in atmospheric science, this is used a lot, and you also know that and you may know, maybe not. There has been a number of published, a number of presented in conference attempts to design subgrid closures in ocean models from data-driven approaches. So basically, approaches where you try to find regularities in correlation in large data sets. Not successful, as far as I know, but maybe Baylor, if he was here, would be able to correct me on the most recent literature in that respect. So, you might say, and that's one of my last slide, I swear. You might say, well, okay, look, that's nice what you're saying, but I'm a physicist. I want to understand things. There's no point having something efficient if I don't understand what I'm doing. Okay? Now, think about this particular model that we're calling the eddy diffusivity. What is it? So that's a model that's obviously central to a number of our closures. What is it, really? This is a statistical fit. A fit between a flux and a gradient. It has weak or hardly any physical basis. Okay? You can find some n-waving kind of argument and explain that, yes, obviously that's how it should be. But that's just an observation. Okay? That's just a happenstance that we turn out to model with a statistical model. Okay? So we've been doing that for years. We should accept that. So maybe, I guess that's what I'm giving here. Maybe we should think of our models being fundamentally a mixture of inference, statistical inference plus physical understanding. And the statistical inference can help you build the physical understanding and vice versa. You can improve your statistical inference procedure with the physical understanding. But we should not keep the physicists on one side and the people involved in that assimilation on the other side. And that's what's happening now, and I think that's great. And just for you to think a bit about that, you might have seen this paper, I don't know, this was published 8 years ago in Science. It was kind of a big paper at the time. So basically what those people did, they said, well, would that be possible to estimate what are the evolution laws for a dynamical system from data? Okay? So they took the simplest system they could think of, so that's a double pendulum. So that's arguably a low-dimensional kind of system. They run it a large number of times. They built a basis combining all possible correlation of the variables, their change in time, blah, blah, blah. And they try and estimate a model. And it actually works. So for this particular model, they were able to find the equations that govern the evolution of the system. Now, think about that from a physical perspective. If you have a tool that allows you to know how your system is evolving. As a physicist, that's great. I see terms, then I try to understand what those terms mean. So that's obviously a fantastic tool for investigating the physics there. Obviously, this is applied successfully for low-dimensional systems with perfect observations, which is hardly the case for the ocean, which is a fantastically huge system and that we're observing imperfectly. So the question I'm asking is whether this kind of approach could actually bring something to oceanography, and I think we will see in the next 20 years whether this is happening or not, but I'd be very excited to see what's the answer to those questions. Conclusions. We've illustrated during this lecture how several aspects of what I think is the ill-posed nature of the deterministic approach to geoscientific modeling and ocean modeling in particular. We've shown, or at least I've said, I haven't really shown that, that stochastic closures are a promising approach for reducing ocean model circulation biases, but that it's a broader method that allows you to actually deal generically with all kind of source of uncertainty, and that ensemble modeling plus stochastic closures can help you understand physical drivers of the low frequency variability of the ocean. That more generally, if you accept this idea that we're describing PDFs with those models, then this strongly advocates for the idea that we should take models and put them in the Bayesian framework and accept for once that we're just modeling probability distribution of possible states of the ocean given our physical knowledge, given the observations, and the uncertainty on the observation and the physical knowledge. And I've just asked whether we think or not, and that could be a matter of debate for lunchtime, of whether data-driven approaches could change something to oceanography in the future. I certainly don't know, and I thank you for your attention.